Okay, let's talk more about ideals. I have just written down the definition again. Let R be a ring. Written is slightly differently, but it's the same thing. Let I be a subset of R. Say that I is a left ideal of R if x in I and A in R implies A times x in I. So when you take an element from I and an arbitrary element from the ring, not necessarily from the ideal, and multiply it on the left with x, the result is still in I. And there's a similar definition of a right ideal. Right ideal, in that case, you say xa in I, and then there is a notion of two-sided ideal where you say both. Please don't. Two-sided. If xa is in I and ax is in I. Let's not try to cram this in. And ax is in I. So if it's a left ideal and a right ideal. And in a commutative ring, they're all the same. And we'll just call them ideals if it's a two-sided ideal. Okay. And then examples. Maybe first examples. R is still a ring. So if you just take the zero element, that always is an ideal. R is always an ideal. So maybe we'll use a notation. I triangle left R means I is a two-sided ideal. In R. Okay, that will be the notation. So that's just the zero guy is an ideal. R itself is an ideal. So these are sort of the trivial examples. The main source of example is kernels of homomorphisms. So let's write down that completely. If f from R to S is a ring homomorphism, then the kernel of f is an ideal, a two-sided ideal in R. This was the content of the lemma we proved last video. So since you have seen many examples of ring homomorphisms, you have many examples of ideals now. Just compute the kernels of those. But we can write some down explicitly. A special kind of ideals that we'll often see are what are called principal ideals. So these come like this. So let A be any element of the ring R, then let AR mean all multiples of A. So all things that look like A times R, where R is some element of R. So you take A and multiply on the right by any element of the ring. So in other words, all multiples, but I don't know if the ring is commutative, so I'm just putting it all the right all the time. So you verify, and this is a very straightforward verification, that AR is a right ideal. Similarly, Ra, by which I mean all these things, R times A, where R varies over R, is a left ideal. So if R is commutative, then this is they're the same thing. Then we write there's a notation that the book uses. They just write it parenthesis A. And this ideal is called the principal ideal generated by A. We say that A is the principal ideal. I can hardly read that. Principal ideal generated by A. An ideal is called an ideal I in R is called principal if I is of the form A for some A in R. Okay, so we have this notion of a principal ideal. And while we are at it, maybe I'll introduce one more word, a commutative integral domain. I guess integral domain already meant commutative. Is called a principal ideal domain. It's been a while, so I'll remind you. Our integral domain just means that two non-zero things cannot multiply to the zero element. Commutative integral domain is called a principal ideal domain, or a PID for short, if every ideal in this thing, let's give it a name, a commutative integral domain R is called a principal ideal domain, or a PID, if every ideal in R is principal. Okay, so we have one more new word, PID. PIDs are particularly nice kind of commutative domains, and a lot that we learned in chapter 1 and chapter 4 about Z and polynomial ring in one variable over field will generalize to PIDs. In particular, the first lemma that we'll prove is Z and Fx are PIDs. Here, let F be a field. If you don't want to think about arbitrary field, just think F equals Q, or real numbers or complex numbers or something like that. Okay, so these are PIDs, which means that I now told you what are all the ideals in Z and what are all the ideals in the polynomial ring in one variable. So the ideals in Z before the proof, so the ideals in Z are things of the form A times Z, where A is some integer. That's not that interesting, I suppose. So, for example, 3z is an ideal, which just means all multiples of 3. Yeah. And obviously the ideal generated by minus 3z would also be the same thing, because all multiples of minus 3 is the same as all multiples of 3. So the ideals in Z are 0 times Z, which is just the 0, 1 times Z, which is just Z, and then 2 times Z, which means all the even numbers, 3 times Z, which means all the multiples of 3, 4 times Z, all multiples of 4, and so on. These are all. Okay, and similarly, the ideals in Fx are of the form all multiples of a particular polynomial, where Fx is a polynomial. Yeah. There again, multiples of x, that would be an ideal. Multiples of x squared plus 1, that would be an ideal. Okay, and these are all the ideals. And this lemma requires a proof, of course. I have written it down. Let's see if we'll do it in the next. Maybe I'll just let you read this.